Record to the cloud. There you go. Recording to the cloud. Nice.
Okay, we good?
Yes, we are good.
All right, so let's get started. Today we're going over our highly anticipated neural net workshop. And neural nets are they're pretty complicated and there's a lot of different variations of them. So we're splitting this GA into two parts. So let's get started. I realize the date on this thing is wrong now, but oops. Okay, so the basic structure of a neural network. So of course, because this is artificial intelligence, everything in AI really is trying to model after the human intelligence, right? So neural networks are modeled after neurons in the brain. So it's just artificial. So there's another type of neural network called artificial neural networks, and like that's where it comes from, because it's not a neural network like in your brain, it's just artificially made. So neural networks have an input layer, which has input neurons, so you can have multiple different types of input. So if you see on this picture here, we have, okay, so these input neurons are part of the input layer, and then these hidden neurons are part of the hidden layer, and the output neuron is part of the output layer. So with the input layer, you can have multiple input neurons, each with different types of like input. So for example, if you're trying to see like how the effects of like healthy diet and like sleeping and exercising affect your overall health, you could have your input 1 as like diet, input 2 as like numbers of hours of sleep, and like input 3 is like however much exercise you get in a day, right? And then we have the hidden layer. So we call it the hidden layer because we don't really like see what's going on in it, but every neuron in the hidden layer processes input. So, and you can just add on more and more hidden layers for more complexity. So, and the output layer has the output neuron, right? It just, gives you your output. So you can also have more than one neuron in this output layer. So like if we were trying to see how sleep and exercise and diet affected overall happiness and overall health, or we could split it into like physical health and mental health, then we could have two output neurons, one for physical and one for mental health. Or if we were just looking at physical health, we can just have one output neuron that outputs, how your physical health is affected, right? So, and the next thing is a synapse. So just like in our brains, we have like neurons and the synapses between them, right? So the synapse with an artificial neural network is the pathways between the neurons. So like all of these arrows are synapses. And yeah, neurons are just like functions. They take output from the previous layer, or for the input layer, you take input like the data, raw data, and then it returns a value. And then it passes it on and passes it on and processes it and processes it. And eventually you get an output. So every neuron they always weigh the input differently, and they always well, of course, all of them are like different functions. You can think of them as like little functions. They just process and process and process. So notice that the nodes in the same layer are not connected. So you don't connect input layer to input layer. Well, obviously, because you don't connect two different types of data input, but you also don't connect hidden neurons to other hidden neurons. What you do is you get everything from the previous layer. So remember, we have the input layer, the hidden layer, and the output layer. So all of these. So for example, our input layer neuron sends its input to every single node in the next hidden layer. And then same for the other input neuron, sends it to every single neuron, and so on and so on. So every node sends it to the next one. Every node sends its output to every node in the next layer, if that makes sense. But they don't send it to each other in the same layer. Okay.
Okay, so our types of neural nets are, our main types are an artificial and convolutional neural network. An artificial neural network is like really the formal, oh dang. It's okay. Okay, artificial neural network is like the formal one, and then a convolutional is a type of artificial neural network. It's a deep neural net. It's primarily used for image recognition, recommendations, NLP, blah, 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 blah. This is like your most common type of neural network. So, for most applications, you're going to see these being used. If you're seeing a neural network in action, usually you can guess, and it'll probably be an ANN or a CNN. It's composed of neurons, like Tiffany was saying, and these have connections, and they basically, on those neurons you have weights, and on the connections of the neurons you have weights. And I mean, we'll go through this picture at the bottom in more detail, but basically what you're doing with this, you're taking a data set and you're kind of, I mean, like, I guess you're convoluting it. You're basically like taking it and making it smaller. You're compressing it, and you're summing data points. And then what you're going to do in the end is you're going to take the data you receive from this, because basically what you're doing is like with a neural net, you are taking a large amount of data and you're making inferences about that data based on like samples, like sample sets of that data, and you're minimizing it. And then after minimizing it enough times, at the end, like you can see on the right hand side, you know, like we start out and we have like, I mean, like you can see like this big volume. So let's say our big volume is like, you know, a picture, you know, like this is an image of a car. Okay, as we're moving to the right, you can see the complexity is decreasing. So we start out and we have this big volume, and we're taking smaller and smaller bits of that, and we're analyzing smaller pieces of you know, the total information being the image that we have of the car. Okay, and what is happening here is that your neural net is basically taking the highest data points, and it's adding these, as you can see all the way on the right. It's basically taking all of these and it's putting it into
Joaquin? Are we good, or is it my Wi-Fi? Well. Okay, Joaquin's Wi-Fi cut out. I guess, you know what, I'll just pick up where he left off, so hopefully he can reconnect, but if not, well, I, oh, guess I might as well do it myself then, okay. Anyway, so Joaquin was saying, you have your input, which is a picture. Convolutional neural networks are typically used for image recognition, although, yeah, he did mention earlier that you can use it for like recommendation in NLP, but most often they're used for image recognition or image compression sometimes. So what you do, because you have an image and you have a ton of pixels, right? And sometimes they're in color. But actually, we're going to cover this in more detail later. But for a brief overview, what you're trying to do is you're trying to make that picture into something, break it into smaller pieces that makes it easier for the computer to process, right? So in that way, we convolute it by, okay, this gets into a lot of linear algebra, but we basically take like little groups of the matrices, like we split up the image into a bunch of tiny little squares, and then each of the squares corresponds to, like, say you have a 3x3 square, and then, oh, Joaquin, are you back?
Okay, yes, I'm back.
Everything good?
I was like just in the middle of talking, and I'm like, wait, what the heck? Why is Google Slides saying that I'm not here anymore?
Yeah, no, I was like,
okay.
is it my Wi-Fi or is Joaquin gone? Anyways, sorry for all these interruptions, guys, but I didn't really.
So
Yeah, can you just keep going? Sorry.
wait, did you continue?
For a little bit, and then you came back.
Did you continue explaining it? Okay. Okay, so where I was vectors. Like basically you're taking like this, okay, here's how I can simplify this. You're taking some big image or some, like, I mean, you don't really have to say image. You're taking some big thing, data that you can make numerical, okay? And essentially like anything that you can make numerical, you're going to put into that neural net, and it's basically going to take that, it's going to abstract that data to compress it, and then it's going to vectorize that data. And the way it's going to vectorize it is the highest, like column 1, you know, is going to be like your max. It's like your highest probability, which is your guess of what this is. So that's what classification is. It's like, is this image what? So is it going to say, like, maybe column 5 is like a dog, column 4 is like a cat, column 3 is an elephant, column 2 is an airplane, and column 1 is a car. Okay, column 1 is going to be what you're going to move towards, and as your model learns, those places on the vector in that matrix will change. So if you know your data set changes and it gets something, you know, like let's say it was wrong and it guessed wrong, that's not a car. Or let's say it gets a whole bunch of new data and there are some really cool like Teslas and it doesn't really recognize Teslas as cars. They look more like frogs, right? So it's like, okay, it starts guessing Teslas and it keeps getting frogs and it's wrong. It's going to start moving. Like I guess what it sees as frog characteristics, frog variables, or like variables in its, oh, we're going to get to this later, hidden box that it associates with frog towards car, and then it's going to think car. I guess, like, I don't know, it's really weird to like think about this stuff just because it's like thinking about the way you kind of think, I guess. Because I mean, like, I don't know, I guess I'm hoping as a human you don't like get these things confused. It's like, oh, car there, that's a frog, you know. But it's like, I guess getting into the intuition of like, how do you look at a car and then know it's a car? How do you look at a truck and still know that that's also a type of car? How do you look at a plane and think, oh, flying car? You know, I mean, these are things that are like abstract and human, like are like reality. You know, it's like you recognize these things just immediately. You can have associations, but teaching that to a machine is like really like an analysis of like how human brains work, which is why it's a neural net. So anyways, let's go back to types. I'm getting sidetracked. We have a feed forward, which is basically like I mean, like it's just, it has nodes and it's just going like you're not going to have any kind of loop back. Like I think we just looked at this earlier. There's like I didn't even know these existed, but there's a multi-layered perceptron. Usually perceptrons, like as a note, perceptrons are usually, they're going to have a single layer. So you're going to have your inputs, and then it's going to move through a single layer of like nodes, and it's going to get simplified, and then it's going to go towards your outputs. Okay. Perceptrons are your simple, like, you know, most basic neural networks. And it basically just works off of weights of 1, 0, and -1, which is like a yes or a no. And then you're basically doing the same kind of thing. You're going to work through gradient descent, which is like, I mean, I guess like you can really, I mean, like I could kind of like explain the math, but it really is all kind of explained in this picture at the bottom of the bottom right of the page. You know, you have your output, and you're just working through, and you're gonna, I mean, like go through yeses and nos, and you're gonna eventually get to your output. And it kind of works on the same principle with the delta rule. Like you could kind of think about like I'm not sure if y'all were here last week, but the Markov chains we were talking about for reinforcement learning. It kind of works like that. You're trying to look for like a maximum probability, and then the thing with the maximum probability of what it is, you know, whether it be a board, anything, you know, a cat, a dog, a fly, whatever you're analyzing and putting it in numerical data, as it like, I mean, basically really what I mean is like an image, anything that you can analyze. You're basically just moving through that decision tree. Yes, no, Does it have this tree? No, then move over here, so on and so forth until you get to an output. Perceptrons are pretty easy to build, and I'm hoping that we could probably get towards something like that later on, hopefully next week.
Yeah.
But we might, we'll more likely be doing another neural net GA, and hopefully have more people.
Hopefully, fingers crossed. Okay.
Okay, so the pros of a neural net is that we can look back to unsupervised and supervised learning for most of those models that we talked about. They usually are most effective with smaller data sets, right? And you're usually using like, I'd say like most of what's happening is just like a mathematical function. That's not necessarily the case with neural nets. It's usually, you'll have like an assortment of mathematical functions working with algorithm, like as an algorithm to build your neural net and basically make those connections better, to optimize. But the bare bones of it is pretty simple math. And the thing about it is that it can handle regression, like the regression function that we talked about that minimizes error and basically tries to fit a line. If y'all remember linear regression, and classification, basically, it's a pretty simple system, but regardless of it being a simple system, it can make very good predictions. However, as I mentioned in the slide, it requires a number of layers to do this. What does a number of layers mean? It means you're going to need a lot of training data to make this model accurate enough to be able to make good predictions. So I guess like you could put it, it's super good to use a neural net because for most large data sets, it's going to be super good to use a neural net because basically not only is it simpler than using a lot of supervised and unsupervised like just basic algorithms, but like with a neural net, it can like the way it works, the way it functions like our brains, it can get through data pretty quickly and it can make like very effective, what's the word? It can make pretty effective inferences on data whenever it's given to it. It's a simple system. A con, however, is because like it's basically just like it's finding like a maximum probability, like as we were talking about with like the feed. Basically, you're gonna have, as you're adding more data to this, as you're making it more accurate, you kind of have a trade-off that you're not going to really know what's happening in those hidden layers. So it's harder to understand how the machine is processing that knowledge. What is it changing to optimize so that it doesn't see a car as a frog? Like that's something hard to find out. You have to, usually, basically what you can do is you can add specific data points and try to like understand how features are affecting, like if you're analyzing the outputs from data sets, basically you can find trends in what variables are changing. However, really in reality, if you have like if your model is improving, you're usually going to be extracting more. And if you're extracting more, then that means that there's more stuff that's always going to be hidden from you, and you're not going to be able to completely understand that black box of your model. Yeah, I mentioned this is something that like your CPU does. So this is like the guts of your computer. It does like this is like the best way to do most of these kind of computations. But it's very expensive. It takes a lot of energy on your system. This is fast calculations, but this is also like expensive in power. You can think about that stuff. But also another thing about it is that it's very efficient for what it does compared to simpler algorithms. So yeah, I don't know. Pros and cons. Okay.
Yeah.
Right here, you can see a neural net. Like as I was. Oh, is this yours?
No, it's fine. You can take it.
Like here, you can see as I was talking about, you have these inputs. So let's say like if you're trying to understand those hidden variables within the hidden layers, like you're trying to understand what like H2 is doing, right? So let's say like the first node in H2, okay? What you're going to do is you're going to feed in different inputs, and you're going to try to see. I mean, like you won't be able to specify that node, maybe, but you can work down and try to understand how a specific node, in that neural net changes whenever you feed it different data points, and you're going to see that in the output. So let's say I feed it a duck, and then I feed it a duck with a hat on, and then I feed it a duck with like a little unibrow, and then I feed it a duck with like a slightly dented bill. I'm going to get different ideas of the independent variables in my hidden layers by what comes out. So the dependent variables that I'm going to get, as like my output, I'm going to understand what's in that hidden layer. But yeah, this is like the build of it. You can see right here, you can see the connections, and then our nodes, and as you saw beforehand, they're basically going to have different weights. So your output is going to decide like how useful each of those nodes are in the hidden layer. Okay, so this is the simple model that we were talking about. Basically, as I said beforehand, there's no hidden layers. You're going from input to output, yes or no. It takes an input, and then, as it says, it calculates the weighted, takes input, then calculates weighted input per node. Yeah. So basically, I think, Tiffany, what you're saying right there is it's taking the input, and then like from the outputs that it's getting, that's how it's going to weight its nodes, right?
Yeah, pretty much, I think. Weighted input.
Okay.
Yeah, so I think what this really means is that different inputs are weighted differently depending, because like if you're trying to do like classify an image and you have your input as like you can have your input as like, okay, let's say you have an image in black and white, and your black pixels are 1 and your white pixels are 0. So I guess technically you could feed it as one image matrix of zeros and ones, but you could also split it and feed it like as black and then white in one of them. And you're probably gonna weigh the black ones more because that's like what your image is, right?
Yeah.
Although technically, if you're doing image processing, you normally feed your image all at once in one like matrix. So that's kind of a bad example because you wouldn't really do that, but that's kind of what I mean by like the input is weighted differently. So like certain things will have more effect on the output than other.
Yeah. But I mean, like basically, I mean, like just continuing on with this kind of system, it's basically just like it's like a, I mean, I guess it's kind of like making like Boolean decisions. So it's
Yeah.
like you have ands, ors. Basically you're answering the question. Is like this. I mean, is this thing like you're? I mean, I guess a way I can phrase this is like your node is asking a question, and if it's true, if it applies, then that node is going to have a greater weight. And you're going to keep moving towards that kind of node. If it's a node, you know, if it's answering like false, that node has less weight for that prediction. Yeah, I don't know. Perceptrons are, I mean, that's the simplest model that you can really build. So I mean,
Yeah,
it's just going to be basic Boolean. Yeah.
Yep.
Okay. Feed forward. This is kind of working on like the same principle. This is, I mean, like these, basically, these include perceptrons. They don't cycle. So as you could see with the perceptron, we're just going from input to output. Cycling meaning that it's not going to, like, you know, get somewhere and then think, okay, I guess the best way I could word this is like, if the question that's being asked by the node, like let's say like from node to node by the connection, if the question that's being asked applies less than the previous question, then the neural net will cycle back. So the neural net will ask like a previous question again, so it can go towards a different route. But these are fully connected, and they work on the same principle of the logistic function, which is basically like, I mean, I'm pretty sure the way it functions in this is kind of like a step function, really. So I'm pretty sure, like going forward, it's like I'm pretty sure it's like the minimum and maximum values of the logistic function in a graph. So I mean, it's basically, you could think of it like a binary. It's like it's either 0 or 1. And then the whole entire model takes place on that kind of scale. You know, you're going to have all of your, I mean, like all of your probabilities are going to be on that line, the logistic function. But this has applications in data compression. You can basically figure out, you know, like which segments of your data are most important from this, and then have those put into a smaller, you know, image or something, let's say. You know, I mean, like, I guess you could say, like, if you're like, let's say, converting a file, you know, and you're doing like a JPEG to a PNG, you know, like this is kind of like something that you would do. Basically, you're trying to find like you're taking the data of that image, and then you're trying to find the parts that matter the most, and then like you would cycle back to, I mean, I don't know. I feel like this is kind of like a lacking analogy, because I don't think you would use this for like an image data compression. I don't know. Do you have any better? I mean, like I feel like that one doesn't really work.
So feed forwards are like the simplest neural networks, because with neural networks, like Joaquin was talking about earlier, to make them more complex, or you cycle backwards. So like with feed forward, it's exactly like the name. It feeds it directly forward, and it doesn't backtrack. So with the data compression, yeah, okay. See, you could do all of these with feed forward if you really wanted to, but there are a lot of other neural network algorithms that do them much better. So like computer vision especially, and like yeah, data compression, not really. I mean, they'll work if you really want them to, but
yeah,
not necessarily the best example, because feed-forward loops, it's really, it's one of the most simple neural nets, so really
but
it
yeah, I
has to be
mean,
used
takeaway
for,
is that it's
yeah.
basically, it's just, I mean, it feeds forward. Okay.
Yeah.
Anyways, going on.
Okay, so convolutional neural networks is what we're getting into. So this is mainly used for like image classification. you have an input image and you assign weight to like the objects or aspects in the image, right? And so you want it to be able to differentiate between like things in the image. So how they can do that is they can do with like color, or they can do like saturation. You know how your pixel has like color values, right? Like the RGB, stuff like that. So that's how it differentiates between like the image, because really your computer, as it sees the image, it can't make sense of it. It breaks it into matrices, or just one big matrix of like either the color values, or yeah, mostly just the color values, and it tries to pick out like edges and places where the color is maybe darkest or lightest, and like the contrast between them is what it really looks at. So it doesn't see images like we do. So like if I saw a picture, like Joaquin was talking about earlier, if I saw pictures of like Teslas and cars, I'd be able to recognize that was a car. That was a car. But like if I saw something else that was like kind of ambiguous, like how is it supposed to know what the difference between a truck and a car is? Is it like the angularness of it, because you know the truck has that like back thing that's like more rectangular, or is it like the size? But that's another problem, because size in pictures is really hard to differentiate. So because of course you can take a picture from like far away and it'll be like a tiny truck next to like a big car, or you can take it like, I don't know, perspective matters a lot, and it gets pretty complicated. But back on topic, for convolutional neural networks, you don't need to really pre-process data too much, because again, it takes input as images, right? So you don't need to, really break it down, because it already kind of does it for you. So it's inspired by the organization of the visual cortex, like in your brain. So like I said earlier, AI of course is, artificial intelligence. So everything we're trying to do here is trying to replicate what our human minds can do. And in this case with convolutional neural networks, because we're trying to either classify images, or like computer vision or image recognition, stuff like that. It has to basically it looks like the organization of the visual cortex in our minds. And it's much more accurate than the feed-forward neural network. So like we mentioned earlier with the feed-forward network, yeah, it can be used for computer vision and stuff like that, but it's best to use a convolutional neural network for this kind of stuff. So there's a lot of steps to this kind of neural network, and it's fairly complicated. It's one of the more common ones, and yeah, it takes a little while to get your mind around it. So actually, in the what was I gonna say? Sorry. Because we're kind of like, oh wow, it's already 9:40 and we still have to go through all of convolutional neural networks. Joaquin and I decided to split this GA into two parts. So we have neural networks 2 next week, and we'll be going over convolutional neural networks more then. But for now, let's just keep going. So we have different steps in the convolutional neural network process. So we have to convolute the image, then we do pooling, flattening, pass it through the connected layers, the receptive fields, and there's weights and biases. All of that comes into play. And this image over here, this is just how it breaks up the image. So the reason we have 3 dimensions typically for images, because they don't have like depth to the image, right? Well, I mean, we have depth perception, we can kind of see that, but normally they break it into like red, green, blue, like the RGB values for that. So every pixel, because if it's in color, it has the RGB value, so that's what it's breaking it up into. And then it moves along the image, and then it keeps moving on and on and on. So this image is slightly misleading because it doesn't go down here and back. So it goes from the top left corner to the right, and then instead of going down and back to the left, it goes back to the left and goes over again. And this will make a little bit more sense with the visual that we have next. So actually no, in the image that we have after this one, sorry. Joaquin, did you want to explain this one or no?
Oopsie. Am I here?
Yeah.
Hello? Hello?
Hello?
Okay, so basically what you can see here is like what I was explaining beforehand. You have your input, which right here is something that we can make numerical, like this image. We're basically going to take it and we're going to take subsets of that data. And we're going to convolute it. Convolution is basically like a linear operation. So this is like making a matrix out of the data in that set that we're taking, that subset, and we're doing matrix math, addition, and multiplication to basically find. We're going to associate a value with that subset, okay, and then we're going to get we're going to repeat that, and we're going to pool all of those data sets, and then we're going to do the same thing again, and then we're going to repeat that, and we're going to pool it. And we're going to keep doing that for all of the layers of this neural net. We're essentially breaking it down into those small pieces. And then once we get here, we have flattening, where basically what we're going to do is we're going to take all of that data, and we're going to actually, I should probably expand on this too. You can see down here it says convolution plus ReLU. I think this stands for, what is it? It's I think it stands for, I don't know. Okay, I could basically explain it while I'm going. Oh, nonlinearity. So it's like a nonlinearity function. It stands for rectified linear unit, which basically means that whenever you're doing this, using that matrix math, you are basically taking all of the elements and condensing them linearly. However, not all of those elements are able to, not all of these subsets. I feel like I probably need to go more into this next GA for like the math side, just to clarify. But basically, whenever you're doing convolution and you're doing that matrix math, that's a linear function to reduce the data, okay, for your feature learning to go into your next layer. However, along the way, you're missing out on nonlinear data. So what you need to do right there is basically you need to have some kind of function where you can reduce that data non-linearly, and this is what you're going to do with rectified linear units. Basically, it's using things like the TANH function. You're going to be using sigmoid and like cinch. I'm not sure if y'all have heard about these things. I mean, it's like hyperbolic functions. You're using hyperbolic functions and you're using sigmoid to reduce nonlinear data. Okay, so you the data in your subsets, and then once you get to the end, because basically what the ReLU is doing is it's making that data linear. So once you get to the end, all of your data is linear. You can put that into a vector. You can put that linear data into a vector. That's what flattening is. Kind of how I was talking about beforehand, basically what you're doing with this is your vector with the flattening, you're going to have your greatest values at the top and your lowest values at the bottom. And you're trying to find a maximum for this function. You're trying to find your best prediction, like as you can see right here, car, truck, van, so on and so forth, all the way down bicycle. You're trying to find your best prediction and know what this thing is. So what you're doing is you're flattening your data, okay, and then you're gonna, it's all connected. It says fully connected right here. But basically, I'm guessing this is just, this step right here is basically just saying like you're linearizing all of your data and putting it into that vector. And then softmax, what softmax is doing is it's analyzing all of that data. And I'll get more into the function next time. It's basically you're taking like a log sum of all of the elements in that vector, and what you're going to do is you're going to try to find a max. You're going to approximate a max for the function of this vector. It's super, like, I don't know. There are a lot of big words to this, but I feel like if I had like a couple of pictures, I could probably make it sound pretty simple. Because I don't know, it's like maximizing, the vector function and blah, 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 blah. But it's really just like you're taking this vector and then you're organizing it with a math function. And then once you organize it, you're going to have probabilities, best prediction to lowest prediction at the bottom of the vector. I feel like that's the best way I can put it,
Yeah, and we'll get into this next time too, but in the interest of time, we're going to move on. Is that okay?
Yeah.
because I still have to get through like all of the feature learning stuff. Okay, let's get going.
I'm sorry, I take way too long.
Don't worry about it. It's fine. But yeah, so let's talk about the convolution layer. So to this original image, like you can see this very nice GIF that I found online. So there's a kernel or like a filter K, and we're applying this to the picture to get a simplified version of the picture, right? So we're basically just trying to simplify it down so we can have something that's easier to process and easier for the computer to understand. So it reduces data and it also conserves computational power, right? So first of all, all the pixels get converted to values and then you extract the high level features. So by high level features, I mean like, if you had like a picture with a dog in it with like grass and like blue sky behind it, the high level features are going to be like the edges of the dog where the contrast is the highest. Or maybe it could also be the contrast between the green grass and the blue sky. So our high level features are what the computer recognizes as areas of contrast, because if you have a large like big chunk of like blue sky, it's not really like a high level feature. That's kind of background, right? So yeah, and in this case specifically, we're applying the kernel or filter K of with the matrix 101010 and 101 again. So you can see how it goes through the image, right? We have a 5x5 and we're turning it into a 3x3. So we have a 3x3 matrix with the filter, and then we're applying it over across this image to get all of this convoluted image, right? So yeah, essentially the convolution layer takes the original image and it just makes it into a simplified version of it with a filter. Yep. Okay, so for color pictures, because the previous one was probably meant for black and white image, but for color pictures, of course, you have your RGB values, so you have red, green, blue. And then for all of these, we're gonna do exactly the same thing. So the way it applies the filter is it goes from the top left corner and then it moves steadily to the right, and then it just starts over at the next row, at the next leftmost element in the left row, if that makes sense. So basically it's doing what you see in this picture right here. It goes to the right, and then it goes down one, but back to the left, and then it goes again. So you have all of these, right? You have your RGB values, and then to convolute this color image, what we do is we combine the RGB values, and then we get an output that has one single value. Because technically you have every picture that's color has like 3 matrices. So if you remember from this earlier one, the reason we have that depth is because you have that R, G, and B filters. And yeah, again, this image is slightly misleading because it doesn't go like down and back to the right. It goes to the left and then back and then back again. But yeah, anyways, so oops. Yeah, so this is for color pictures, which obviously most pictures are, because what's the use of a neural network if it only works on black and white, So yeah, this is how we would convolute a color picture. And then of course you get your output with a convoluted image, right? Simplified version of your original image. So next, after we can convolute it, we pool. So this is called the pooling layer of the process. And you can either there are 2 types of pooling, but I'll get in that in just 1 second. So essentially it reduces the size of the convoluted image. So if you remember, the convoluted image is essentially the image, but simpler. So like, it's not so high def, right? That's kind of it. And then the pooling layer just makes it smaller, easier to process. And it also is useful because it extracts dominant features, kind of like how the convolution layer does it. But a pooling layer also is a useful place, not useful, also it's a good place to extract dominant features from. So with the 2 ways we can do pooling is we can do max pooling and we can do average pooling. So if we have this convoluted image that was passed from the convolutional layer earlier to us, we're trying to, okay, we have a 4x4 right here, and then we're trying to break it into a 2x2, right? So we're going to split it up, and every quadrant corresponds to a quadrant in the 2x2. So like you see these, yeah, it's pretty straightforward. Like, So for the max, you're going to take the max value in your quadrant. And for the average, you're going to take, the average. So you have this matrix that results from max pooling and this matrix that results from average pooling. And the max pooling is actually contrary to your intuition, because if you're thinking, wouldn't the average perform better than the max because it's a better representation of the data as a whole? Yeah, that's what I initially thought as well. But actually, the max pooling is the one that performs better. And this is because of the noise suppression. So there's going to be like noise in data is like kind of what it sounds like. Like, if your data is like messy or like it reduces like lots of like little variations in your data, kind of, if that makes sense. So with the average pooling, it reduces the dimension and it uses the averaging as the noise suppressing mechanism. Like average pooling doesn't have another specific noise suppressing mechanism. It is in itself a noise suppressing mechanism, but not really a good one. And with the max pooling, they take the max number and they have, sometimes you apply other noise suppression mechanisms, but this one typically performs better because it has a method of pooling that's separate from the noise suppression. So the average is the average and the noise suppression like together, and like the averaging is the noise suppression and is the method of pooling. But with the max pooling, you have two different like methods. You have the taking the maximum for the pooling, and then you have the noise suppression. So it typically ends up performing better. And another reason this does perform better is because with your pictures, your max feature in the picture is like your highest value, right? Oh, obviously highest value, but in your image, like it's much easier to tell the difference between black and white, right? But if you were averaging it, it would become more like gray, kind of. So um it like amplifies the original feature. So if your original dog was like brown or something, it might take the max pooling as like black, but if you average it, it might become like some sort of other stranger color, I guess. But basically, it takes the most prominent features and then that's what it rolls with, the most prominent features of the photo, not the average. Because when you average a lot of the pixels together, sometimes it gets blurry, if that makes sense. Okay. But yeah, for pooling, essentially remember that it's just making it smaller. After we convolute the image, we need to make it smaller and easier to process. Because if you think about it, a lot of pictures are like, have a lot of pixels. Like, what is the standard photo? It's like, I don't actually know, but it's like well into the hundreds, I think. Like 700-ish something by 700, I don't know, or like 1080 times something else. But essentially you have a really big matrix with a lot of pixels, right? Because if you're breaking up your picture into individual pictures, and now I'm sure with like the high def cameras, there are bigger matrices with much more elements. So you need to feed it through, like, you need to convolute it and pull and convolute it and pull and do that several times until it's into a matrix that is easy to process, right? Okay. And then after we do all of that and we finally pare our data down to a manageable size, we do what's called flattening. So we have our pooled feature map here. And then by flattening, basically you're taking this matrix and then you're turning it into a vector, like Joaquin explained earlier. So if you can see, like, all these all these elements of the matrix get shoved all into one. So originally it's like a 3x3 matrix, but now it becomes a 9x1 matrix, or in this case, a column vector, right? So yeah, and then another image, you have your layers, your pooling layers, and then you just flatten it all into one column. And then that's what you feed your convolutional neural network. Well, okay, you feed your image initially, but process it and process, and before it actually starts to do any of the recognition and any of the identification, it takes that image, breaks it down, and then flattens it. And then with that flattened data, that's what you're looking at to try to determine, like, is this a car? Is this a Tesla? Is this a truck? Or is this a frog? So Yeah,
I love
and
that example.
yeah, the Tesla frog example is pretty yeah. Um, okay, so I think we're gonna stop here for now for convolutional neural networks because we discussed all of the like kind of pre-processing of data it does, and then we'll get into like the actual stuff it does, like this classification area, because we talked about convolutional step layers and like pooling and all this stuff. Then next time we're gonna finish and talk about like the well, we talked about the flattening. We're gonna talk about how it actually like processes the flattened data and the softmax function. And then, yeah, or probably there's a lot more to neural networks than what we covered today.
Would you be able to go to the very end?
Oh, yeah, sorry.
Uh, well, I mean, like just to clarify, like what I was saying beforehand, this image kind of like takes the cake to like explain what I was like really trying to say with the softmax function. You can see it right here. It's basically like a sum of the k. So you have like the what is it called again? K.
The kernel filter?
Yeah, there you go. You have the kernel filter, and it's basically it's taking the elements and it's going through them and like doing like a sum. I mean, you can kind of see this, but basically, you're taking all of these, you're summing them up, and then you're finding the largest ones. You can see right here, green has the largest probability, and then so on and so forth. And I mean, it's labeled as such. Your max, the soft part comes from. I think it works on it also works on like a sigmoid function, which is I think that's why it's called soft. I'll have to go more into that later because I'm kind of fuzzy on that. But the max part is kind of obvious. Basically, what you can see right here is on the right. You're maximizing your probabilities, and then green probability is what your model would guess this data to be. You know, so whether it's an image or whatever, whatnot, that's its guess of what it's looking at. Yeah, that's about it.
Yeah, so, um, yeah,
We
this is
are
a good beginner introduction to neural networks, and we're going to get deeper into this probably next week. There's a lot more we haven't covered yet. But yeah, that's a good general understanding of how neural networks work. Okay. Any questions?
if yeah, I know I was like super unclear about the stuff,
Yeah, I was kind of unclear sometimes too. Sorry.
and everything. So if y'all have any questions and y'all want me to go back, I know I kind of also messed up on like feed. For feedback, or not feedback. God dang it! Why do I keep messing up that name? Forward feed forward.
Feed forward.
Yeah, I think I messed up at some point, and I said like I was making like I was contrasting it with like a model that would feed backwards as
Oh yeah, the
opposed to
back
feeding
propagation.
forward. Yeah, back propagation does not equal feed forward.
No. Feed forward. Yeah.
it
Feed
is the
forward
exact like
specifically feeds forward and does not do any of the back cycling or back propagation. Yeah.
I don't know. Do you have any like examples of what like I mean I feel like I kind of did that like wrong. I didn't do it justice. Do you have like any examples of back propagation? Because I mean I'm not really sure.
We can probably talk about that next time because it'll take a while. But essentially, what you're doing with your hidden layers, you have your input and your output layer, right? But your hidden layers is, where all the magic happens. So you're feeding it forward through all your layers, right? But with the back propagation, instead of simply feeding it forward and moving on from layer to layer to layer, you also are simultaneously feeding data like back and forth, kind of. So it's not like a chain of neurons. It's like yeah, like the neural networks look like this whole like big mess of like neurons and maps, but with back propagation, essentially you just kind of feed data. You're feeding data forward and backwards, if that makes sense. Like a linked list.
Yeah.
Okay, yeah, but we'll get into that next time with like we'll get into that deeper next time because that gets into kind of more advanced applications of neural networks. But yeah, we'll get into that.
If y'all are shy, you could do like yes or no. But if like, would y'all want us to like release slides or like any of this stuff so like y'all can check it out on your own time? Would that be helpful?
Yeah, I forgot to post the recording for last week.
Okay.
Oops. Post that
I'm
and the
not
time activity.
sure. I'm hoping at some point we can like post these in like maybe an unlisted YouTube or I don't know, maybe a
Yeah,
private YouTube.
we should
Like
start a YouTube
risky.
channel, but we also steal a bunch of pictures online, so
Yeah, I'm not sure how
they'd
that would
like.
work out for us, but hopefully no one would notice and we could just kind of go about our lives.
Yeah.
But it'd be nice if we could have like these resources up, you know, just for like y'all to, I don't know. I'm not sure who like future execs will be or anything like that or how any of that stuff's going to go about. But I'd like to have these resources up and hopefully like make a trend for this club that like we
have like
we
a
keep
actual
archive.
website.
Yeah, I don't know. I feel like it'd be hard to put them on a website. I feel like I mean the website is we've already procrastinated the
Yeah,
website.
okay, we were
like
supposed to make a website at like the
a
beginning of the
whole
year.
month.
Nothing happened. That's a
I don't know.
crafter jobs.
I'd like to have more resources for y'all.
Yeah.
That'll probably come later this semester though, if I'm going to be completely honest.
Yeah, because honestly, everyone's busy,
realistically,
and I'm sure you guys are busy and don't like. What was the reason we only have 4 people in this? Because everyone's busy. It's test week. Yeah, I understand. And also, it's really hard to like commit yourself to actually showing up to online stuff. Like I don't know. Anyways, but yeah, we'll get more stuff out there that you guys can look at your own time. Yeah. Any questions?
Alrighty.
Mm-hmm.
I hope y'all have a good night.
Yeah. Thank you guys for coming.
Do well on your tests if you have any.
Go. Go forth. Do well on your tests. You guys can do it.
Oh, did you end the recording?
Oh, no.
Nice.
Wow, there's just a recording of us talking about like stolen pictures now, but okay, and our procrastination, but
Nice.
yeah, okay, that's out there. But yeah, thanks.